Hello, I'm Kyle Kevin Delos Reyes. Before we dive into our core topic, we must understand the engine that drives it. The definite integral. In calculus, a definite integral is the mathematical tool we use to calculate the net sign area between a function and x-axis over a closed interval from a to b. Think of this not as a static shape, but the sum of infinitely many infinitesimally thin vertical strips. This brings us to our chosen topic, the sum of different rules. In the real world, functions are rarely simple. They are often combinations of different force and values. By understanding the integrals are linear, we gain the power to split these complex combined areas into separate, manageable pieces. This property is what allows us to move from abstract theory to practical calculations. Now, let's look at how these properties actually look in action.
Hello, I am Ajay Martinez. And so to understand these rules, we must look at the geometry. Imagine two separate functions, the f of x and the g of x. Each carves its own unique territory above the x-axis. And when we add these functions, we aren't just merging symbols, we are literally stacking those areas on top of one another. And the rule states that the integral of a sum equals the sum of the individual integrals. And same logic applies to the difference rule. Think of it as a area subtraction. If you subtract g of x from f of x, you are measuring the gap between them. And this property proves that integration respects addition. The only golden rule is a and b must remain identical from or for every piece of the puzzle.
Let's walk through a step-by-step example of evaluating a definite integral using the sum rule. We are given the integral of 1 to 5, the function 2x plus 3 plus x squared. First, we apply the sum rule. This allows us to split the integral into two simpler parts, the integral of 2x plus 3 and the integral of x squared, both over the same interval. Next, we find the antiderivatives. The antiderivatives of 2x is x squared, and for 3, it's 3x. For x squared, the antiderivative is x cubed over 3. Now, we evaluate each expression using the limits from 1 to 5. Substitute the upper limit, then subtract the value at the lower limit. Finally, we simplify the result after combining all terms. We arrive at the final answer, 68 over 3, or approximately 22.67 square units. This method shows how breaking down a problem using the sum rule makes integration more manageable and efficient. 6-7.
Good day, everyone. I'm Dominic Froyalde Jr., and I will be guiding you through the operational mechanics of our topic. Now that we understand the visual logic of splitting areas, we must address the how specifically how we move from a symbolic integral to a concrete numerical area. To do this, we rely on the fundamental theorem of calculus, or the FTC. We execute this through a rigorous three steps plan. Step one is the search. We identify the antiderivatives and denote as capital Fx for every individual term we have split. This process effectively reversed differentiation using the power rule. And step two is the upper substitution. We evaluate our antiderivative at the upper limit b to find the total accumulation from the starts of the interval. And finally, the step 3 is the difference. We evaluate the function at the lower limits a and subtract that value from our first result. This theorem is the vital bridge between the world of derivatives and the world of geometry. It is the secret that allows us to take an abstract flowing curve and boil it down to one precise, absolute numerical value. And before we conclude, we must address the common pitfalls that often leads to errors and define integration. Even if you understand the theory, those three student traps can compromise your results. First, mismatch limits. The sum and difference rules is only valid if both integrals share the exact same interval. You cannot split a function and then change the bonds from A to on one piece and something else on the other. They must remain identical throughout the entire process. And second, the negative sign trap. When applying the difference rule, the subtraction applies to the entire second integral. A frequency mistake is failing to distribute the negative sign across every term inside the function. Be a sign guardian and, and double check your brackets. And finally, skipping FTC steps. A common shortcut is trying to do the subtraction in your head. Always write out FB minus FA explicitly. And that's all.
My name is Guy Luis Magistrado. To conclude our presentation and solidify your understanding, let's look at the final practice challenge. The integral from 0 to 2 of 3x cubed plus 4x. If you apply the sum rule of we've discussed today, you find the antiderivative of x cubed plus 2x squared. When you evaluate this across from interval from 0 to 2, the total area results in exactly 16. As you continue your studies, keep these three professional quality checks in mind. First, limit consistency. Your bounds of integration must remain identical when you split your terms. Second, be a sign guardian. If your original function has a subtraction sign, that negative must be distributed carefully to the entire second integral. Finally, verification. Always differentiate your antiderivative as a final check. If it doesn't return to your original integrand, a mistake was made in your integration steps. Mastering these rules allows you to decode the geometry of change in physics, engineering, and beyond. On behalf of our entire group, thank you for your time and keep integrating.